Today's lesson is on impulse and momentum. It's a quantity for us that has a lot of practical applications and a lot of practical relevance. But in addition, it also shares a problem-solving technique with the idea of work and energy. So let's take a look here at these two problems right off the bat. And after we show you some problem-solving similarities between these two things, then we're going to talk a little bit about the concept of the idea of impulse and momentum. So as far as problem solving goes, right, and we showed you this yesterday, there's a super direct comparison between what happens with work and energy compared to what happens with impulse and momentum. So let's take a look here. What is the net work done to accelerate a 5 kilogram object from a speed of 3 meters per second to a speed of 7 meters per second? So we've talked here in the past about how we approach our problems. This question is asking for the idea of work. So it would be logical for us to default to the idea that work is equal to F times delta X. That's super logical. It would be easy for us if we had some data on force and we had some data on displacement here. But if you look, we don't have data on either of those things. So in this particular case, we've got two options. We could go try to find F and delta X using kinematics and Newton's laws. And we may or may not be able to do that depending on the problem. There's various ways that we can, but oftentimes the easier route is to go to our main concept. And our main concept in this particular situation is that work is equal to the change in energy. Now, in this particular case, we're changing kinetic energy. So the work done here is equal to a change in kinetic energy. Well, why is there a change in kinetic energy? Well, there's a change in speed. So what is that change in kinetic energy? Well, it's 1/2 m times v final squared minus 1/2 m times v initial squared. So if I factor out that 1/2 m, I get 1/2 times 5 kilograms, and then I'm going to multiply that by the final velocity squared. Well, the final velocity squared is 7 squared, or 49 meters squared per second squared, minus the initial velocity squared. 3 squared is 9 meters squared per second squared. So if I take that, that's 1/2 times 5 times 40, or 100 joules. Now note here that work is in joules, just like energy is in joules. Hence, it makes sense for this idea of work being equal to our change in energy right in here. Now, if we come over here, we have basically the exact same setup. What's the net impulse needed to accelerate the same object from one speed to the next? Well, yesterday, we talked about the idea that impulse, J, is the product of force and time. So we've got two options here. It'd be easy if there was some force data and some time data. That'd be super easy, but we don't have that luxury here. So instead, we've got two options. Well, we can find, just like we did before, we can find F and delta T, again, using kinematics and or Newton's laws. So using kinematics or Newton's laws, and if we're using kinematics or Newton's laws, we could find F, we could find delta T, or our other option, like we talked about yesterday, is impulse is equal to our change in momentum. So you can see the exact comparisons. We've got the same options here for this topic as we did for our last topic. So impulse here is equal to the change in momentum. Now how can any particular object change its momentum? Well, it changes its momentum by changing its velocity. Impulse equals m times delta v. Well, that impulse then, our impulse would then be equal to 5 kilograms. Now my delta V here is 7 to 3, or 3 to 7 rather. So that's a change in velocity of 4 meters per second. So we get an impulse equal to 20 kilogram meters per second. Now, if you're astute here with the idea of what our units are, these units of impulse here, I've got them labeled as kilogram meters per second. Now, in reality, the kilogram meter per second is our unit for momentum. But impulse and momentum are related here, just like work and energy are related here. We talked about work and energy having the same unit. Impulse and momentum have the same unit as well. It's not as clear cut though, because we don't have a derived unit, right? So joule is a derived unit over here. So we don't have to constantly say kilogram meters squared per second squared. We have a derived unit for joule. We don't have one of those for momentum. Our standard unit for momentum is kilogram meters per second. But if you look at impulse, impulse is the product of force and time. So in reality here, this impulse could be 20 newtons times seconds. A kilogram meter per second is the same thing as a newton times a second, because a newton is a kilogram meter per second squared. Multiply that by a second, and you end up with a kilogram meter per second. So you can see that we have some problem-solving similarities between what happens with work and power and energy as opposed to what happens to impulse and momentum. So now on to our concepts here with the idea of impulse and momentum. And there are lots of different subtleties to this relationship. Certainly we can't go over every single one of them, and that's not the design of our course. The design of our course is to give you the quantitative reasoning skills so that you can think on your own and figure out different situations with the basic ideas and the basic concepts. So, we see that here's the idea of impulse. Here's the idea of momentum. And then the key concept is that when we exert an impulse, we change the momentum of an object. So impulse equals change in momentum. So you can mix and match these equations any way you want. F delta T could equal delta P, and how do we change momentum? Well, change in momentum is an M delta V. So these three things have a lot of interchanging and ways that they can be used. And the practical applications of this concept are everywhere, every day, all the time. All right. In fact, every time you take a step on a good shoe, and it's more comfortable instead of walking barefoot. That's an idea of impulse and momentum, and we're going to show you that here in a little bit. So I've picked out two situations where impulse and momentum can be used to explain a concept that happens perhaps every single day, right? So we could talk about impulse and momentum in terms of speeding up an object as much as possible, and then we can also talk about slowing down so you don't hurt yourself. And this has practical applications in car safety. Well, it has practical applications in lots of stuff, but we're going to talk about it in terms of car safety. And then over here, we're going to talk about this in terms of sports. So if you are a soccer player, you want to kick the ball and you want to score a goal. Well, it's easiest to do that if you are kicking the ball as fast as possible. And if you are, Josh Allen in a football game and you want to throw the football to your receiver, it's easiest if you can do that as quickly as possible so that the defenders don't come and catch the football instead of your receiver. If you are a baseball player and you want to throw the ball, if you're a pitcher, you want to throw the ball as fast as you can. It makes it harder for the batter to hit the ball. So how can that happen, right? So how can we increase the speed of this ball as much as possible? Well, first off, if we are going to increase the speed by as much as possible, then what does that mean? If we're going to increase the speed of an object as much as possible, we're going to have a great change in momentum, because your momentum is mv, and therefore, if we're going to change that velocity, if I'm going to take this ball from a speed of 0 to a speed of as much as possible, then we're going to change the momentum of the ball as much as possible. And how do we change momentum? Well, we exert an impulse to change the momentum. An impulse is made up of F delta T. So let's just think about this, right? We can think about this from any quantity, right? So like anytime you have a setup like this, we can use logic to explain it. This can be likened, perhaps, right? Instead of change in momentum, perhaps that could be a change in the amount of money you have in your pocket. Well, how can you change the amount of money that you have in your pocket from a working perspective? If I made $100 last week working and I want to make $200 this week, how can I change that? Well, the amount of money that you make, right? So the amount of money that you make is equal to your wage, $10 per hour, times the number of hours that you work. So if you have no money and you have a job where you make $10 an hour and you work 20 hours, then your change in money is going to be $200. Well, how can you make more money? Well, you can make more money by working more hours. You can make more money by getting a job with a higher wage. So part of quantitative reasoning, right, like this is logic. Just about everybody understands that. We're taking the same equation, we're bringing it over here. So if I want to change this thing, its momentum by as much as possible, I have to exert a bigger force over a bigger period of time, all right, or one or the other, right? So what could I do? I could, to make this big, I could have a super large force. Or I could exert the force for a long time. Or both. Now, what's it mean to exert a force for a long period of time? Well, in a sports setting, it means following through. So if you are a soccer player and you kick the soccer ball, you don't stop your leg when you kick the soccer ball. You follow through and extend your leg when you kick the soccer ball. If you are a volleyball player and you want to spike the ball super hard, you do not spike the ball and then stop your arm. You spike the ball and follow through. When you are following through, whether you know it or not, you are exerting the force for a longer period of time. If I'm going to throw this ball, I don't throw it and then stop my hand. I throw the ball and then follow all the way through. And what that means is that I'm exerting a force this entire time that the ball is in contact with my arm. And if I stop here, then the time frame that I'm exerting that force is small. So we can see an example here about how you can change, or how the situation changes, the variables that you are talking about in terms of force and time to manipulate what your change in momentum is. Now, car safety is another example, right? And these are two examples, but certainly they're not the only example. We are trying to train you to logically think about situations in terms of these quantities. So we want to slow down, let's say, a car so as to not hurt yourself. And if we're going to slow down a car so as to not hurt yourself, we actually have two possibilities. Okay, so let's say this. If we're going to slow down so as to not hurt yourself. So let's think about this. If we want to slow from 50 miles per hour to 0 miles per hour, quickly is one situation, or if we slow from 50 miles per hour to 0 miles per hour slowly. How does impulse and momentum illustrate which one of these things is better for you? All right, so let's think about this. You drive your car. Let's say I drive my car, all right? I have a Honda Pilot. If I drive my car and I'm driving 50 miles an hour down Transit Road, I tend to drive relatively conservatively. And if I see a red light way far off in the distance, I would begin to slow down. I would go from 50 to 0 over a long period of time. My wife, however, loves to go 50 miles an hour until she's super close to the car that stopped in front of her and then kind of slam on the brakes. Right? And then God forbid that someone ever cuts you off and you got to go from 50 to 0 extra quickly. My point here is this. If I drive my Honda Pilot and I go 50 to 0, and my wife drives the Honda Pilot and she goes 50 to 0, then the change in momentum in each situation is the same. The car is going to experience a certain impulse when my wife drives it, and the car is going to experience the same impulse when I drive it. How do I know that the impulse when my wife drives it is going to be the same as the impulse when I drive it? Because the change in momentum is going to be the same. Why do I know that? Because the car is the same. I'm driving the Honda Pilot and she's driving the Honda Pilot, and our change in velocity for each person is 50 to 0. But look at how this happens. What happens? What do I do? Relatively speaking, I slow down over a very large period of time. My wife slows down over a small period of time. Well, if my F delta T has to equal her F delta T, the only way to accomplish that is that I must experience a smaller force, whereas she experiences a larger force. Let's put some numbers into that. So let's just say the change in momentum for both my wife and I when we drive that car is 100 units. I'm going to leave off the units just to make it easy for us. Well, if my wife makes that change in momentum in 0.1 seconds, and I make it in 1 second. Now, 9/10 of a second is not a long period of time, but really we're talking about multiples here. So in reality here, I am stopping over a period of time that is 10 times greater than this period of time. Well, what does that mean? Well, what number times 1 gives us 100? Well, then the force that I would be experiencing would be 100 units. But in order to get a number times 0.1 to equal 100, the force my wife would be experiencing would be 1,000 units. So my wife would experience a force 10 times greater than I would experience. Now, the force is what actually would hurt you in a situation like this. So let's just say, for instance, the seatbelt exerts a force of 100 newtons on me, and the seatbelt exerts a force of 1,000 newtons on my wife. All right. Well, if your skin bruises at 500 newtons, I'm not even close to getting a bruise on my chest, but my wife is twice as great of a force to get that bruise on her chest. So your car's got lots of safety features that do this. The airbags extend the amount of time before you stop and therefore decreases the force, right? Like if you're driving 50 miles an hour in your car and you get into an accident and the airbag stops you, that's a lot better than the steering wheel or the windshield stopping you, because the airbag's going to do so over a large period of time and therefore a small force. The car is designed to crumple, right? If the car is designed to crumple, it's designed so that it stops when it accordions in front of you, it increases the time and thereby decreases the force. There's lots of practical applications that involve these impulse and momentum and impulse equals change in momentum stuff. Right? Here's 2 examples. Now your job is to think about what's going on in practical applications and apply the quantitative reasoning that we have talked about.